In this video, we'll learn the first topic in chapter 3 about second-order linear equations. In the previous chapter, we learned several methods to solve first-order differential equations. In this chapter, we have second-order. So in the equation, we have second derivative. In this topic, I will introduce the general theory of second-order homogeneous equations, and in later topics, we'll learn how to solve those equations. So first of all, let's look at the definition. Recall that a second-order linear equation is an equation that can be written in the following format. We have a coefficient denoted by ax times y double prime plus bx times y prime plus cx times y equals to something on the right hand side, the function gx. We will assume that these coefficients ax, bx, cx, and gx are continuous functions. So recall from calculus 1 that continuous function means that these functions don't have any break, don't have any gaps in their graph. But this is just a technical condition for the theory. In practice, we usually have these conditions, so we are not really concerned much about them. We also assume that ax is different from 0. We don't want the coefficient of y double prime to be 0 somewhere. This is a second-order differential equation because we have y double prime. And for this equation, y is the unknown and x is the independent variable. Initial conditions for such an equation is that because we have two derivatives, second derivative, so initial conditions will contain two things. The first one is something like the value of the function at x0 equal to, say, alpha, and another condition is the derivative at x0 equal to beta. So if you compare what initial condition in first order equations, then you see that we have both the value of the function and the derivative of the function at x0. Now by looking at the differential equation right here, we have the right hand side g of x. There are two cases. If the right hand side here happens to be 0, if g of x is 0 for all x, meaning that the equation is of the form ax times y double prime plus bx times y prime plus cx times y equal to 0 on the right hand side. Then we call such an equation homogeneous equation. Now, you saw the notion of homogeneous first order equation before. Unfortunately, even though we use the same name, the same word, homogeneous, the meaning is completely different here. In this context, the meaning homogeneous means just the right hand side of the equation is zero. So don't be confused with these two notions. So because of that, we will refrain from using the adjective homogeneous too often here. But you should distinguish the difference. On the other hand, if gx is not zero, then we call the equation non-homogeneous. Some people call it inhomogeneous equation. But essentially what it means is that on the right hand side, instead of zero, we have a function of x. These two types of equation are clearly related. However, the first type, homogeneous equation, are easier to solve. And later on, when we solve non-homogeneous equation, we do need homogeneous equation. So we begin with the theory of homogeneous equation, and that the content of this topic here. You see that homogeneous equation. So before doing anything, let's look at an example here. This is a familiar example that we saw in the very first topic 1, in fact. Consider the following ODE. Second order differential equations: x squared y double prime plus 2x y prime minus 6y equals 0. And here we will have the condition on the independent variable that x is positive. The reason is to make the coefficient here different from 0. So first, let's look at a few questions. The first question is, find constant r such that y equal to x to the r is a solution. We did this in topic 1. So to do that, we just take derivative using the power rule. We have rx to the r minus first, and then second derivative will be r minus 1 x to the r minus 2. And to be solution, we plug into the equation. Then we have x squared times second derivative means r minus 1 and x to the r minus 2, and plus 2x times the first derivative, which is r x to the r minus 1. Lastly, minus 6y, which is x to the r equals 0. Simplify this. So we have r minus 1 and then x squared multiplied by x to the r minus 2. We combine the two exponents to get x to the r. The same thing with the middle term. We combine these x, and I'll just mark there. Then we have 2r, and again x to the r, and minus 6x to the r equals 0. We want this to be true for all x. or x positive, that the condition on the independent variable want this to be true or x positive. Well, everything here contains the common factor of x to the r, so we just divide through by x to the r. Then we have r minus 1 plus 2r minus 6 equals 0. Distribute, we have r squared minus r plus 2r minus 6 equals 0. And so we have quadratic equation r squared plus r minus 6 equals 0. From here, we solve for r. You can factor this out. In this case, we have these two factors, or you can use quadratic formula, whichever convenient for you. But as I mentioned in the very first lecture, you should know both quadratic formula and factoring. So 2 and then r equal to minus 3 here. Now, because we have two values, I will label the first one as sub 1, the second one as sub 2. And so we get two solutions. Y1 is x to the r1, which is x squared, and then y2 is x to the r2, which is x to the negative 3. We could turn it into fraction or just leave it like this. So what happens is that we have found two solutions. Y1 is this, and another solution, y2, is this. Now, the second question, are there more solutions? Well, in topic 1, we didn't learn to find more solutions. But in this chapter, we'll learn to find actually all the solutions of certain equations. It turns out the answer to this is yes, certainly, yes. There are a lot more solutions. In fact, anything of the form y equal to c1 times y1 plus c2 times y2. In this case, we have c1 times x squared plus c2 times x to the negative 3 is a solution, where c1, c2 are two constants. So we found earlier y1 is x squared, y2 is x cubed. But if we look at or something like c1 times y1 plus c2 times y2, where c1 and c2 are constant, then everything like this is a solution. And if you learn linear algebra, then this expression is called a linear combination of y1 and y2. Now, in fact, how do we show that? Let me just do a quick calculation here for you to see. Well, why is like that? Let's take y prime. C1 is a constant, so the derivative of C1 x squared is just 2C1x. And we also have the derivative of the second term is minus 3C2 x to the minus 4. Second derivative gonna be 2C1 and plus 12 C2 x to the negative 5. Now let's plug in the equation. The equation is what? We have x squared times second derivative. So I have 2c1 plus 12c2 x to the negative 5. Then plus 2x times fourth derivative, which is here. So 2c1x minus 3c2x to the negative 4. And lastly, minus 6 times y. Y is c1x squared plus c2x to the negative 3. And we want to know, is it true that everything cancels out to get 0? Well, you just do the algebra and see what happens. If you distribute in, we will have 2c1 x squared plus 12c2, and x squared combined with x to the negative 5 will give us x to the negative 3. And next, distribute this, we have plus 4c1 x squared and minus 6c2 x here distribute with x to the negative 4 will give us x to the negative 3. And down here we have minus 6c1 x squared and minus 6c2 x to the negative 3. And we want to check is 0. If you combine the like terms here, c1 x squared, c1 x squared, c1 x squared, what do we get? Everything cancel out, right? 2 plus 4 is 6, and then minus 6 gone. For the other terms, 12 c2 x to the negative 3 is minus 6 c2 x to the negative 3, minus 6 c2 x to the negative 3. Again, they cancel out. And this is a true identity. So this is a true identity. So we have verified that everything like above. So y equal to c1 x squared plus c2 x to the negative 3 is a solution. Doesn't matter what constant c1 and c2 are. Always will have a solution. So by choosing different values of c1, c2, we will have different solutions. So you see that we have a lot of solutions here. Starting with only 2 solutions, we have a lot of them. Here is another more interesting, difficult question: that are there more solutions? So besides this expression, are there anything else? This question is difficult to answer, but it turns out that theoretically, some mathematician has proved that no, there are no more. No. Any solution must be of the above form. Must be of the above format. Must be c1 x squared plus c2 x to the negative 3. And this is true for general second order linear equation as well. This is true for general second order linear equation. Okay. So for any second order linear equations, we can find two solutions, y1 and y2, so that any linear combination is a solution and we have no other type of solution. However, we need to be careful. If you just pick randomly two solutions, y1 and y2, then they may not generate all the solutions. You need to notice that for the previous example, we picked two different things, right? Y1 is x squared and y2 x to the negative 3. If we pick something different, then the two y1 and y2 may not generate all other solutions. So in order to capture all the solutions, we need to look at the following definition. And after writing down this definition, I will show you the fact that we may use later on. Two functions, y1 of x and y2 of x, are called linearly independent. Linearly independent if y2x is not a constant multiple of y1x and vice versa. Equivalently, so y2 is not a constant multiple of y1. Equivalently, the ratio here, y2x divided by y1x, is not a constant function. So two functions are linearly independent if their ratio is not a constant, like what this definition says. Now, if you have learned about linear algebra, then you should have seen the notion of linear independence in linear algebra. For two functions or two vectors, then the definition in linear algebra is essentially the same as our definition here. For three or more functions, the definition, later on when we learn about higher order differential equations, we will look at that. But, all right, so here's a fact about second order differential equations. So consider the ODE, second order, ax y double prime plus bx times y prime plus cx times y equals 0. Then here is the theoretical fact that we will need. If we can find two solutions, if y1x and y2x are two solutions that are linearly independent, then every other solution must be of the form y equal to c1 times y1 plus c2 times y2. So I have dropped the independent variable x here, but we know that y1, y2, and y here are function of x, where c1, c2 are constant. So if we could find out that two things are solution and they are linearly independent, then we can generate all other solutions. It said that every other solution must be of this form. So we have all solution like this. We don't have any other type of solution. This is very important because once we know y1 and y2, then we can describe all the solution. So we say that y1x and y2x form a basis for the space of solutions. And the formula y equal to c1 y1 plus c2 y2, where y1 y2 are two, where c1 and c2 are two constant, is called the general solution. So you see the meaning of general solution. General solution because it captures all other solutions. But again, this linear combination is the general solution only when y1 and y2 are linearly independent. If y1 and y2 are not linearly independent, then they do not form a basis. Some other people say also call that y1, y2 form a fundamental set of solution. We also say that y1x, y2x form a fundamental set of solution. All right. Let's look at another example. Consider the ODE. Y double prime plus 4y prime plus 4y equals 0. First, find R such that y equals to e to the rx is a solution. We again saw this earlier in topic 1. To find r, we just take derivative, so r e to the rx. Here we're using the exponential rule, r squared e to the rx, and then we plug into the equation. Then we have r squared e to the rx plus 4 times the derivative, so 4r e to the rx plus 4 times y, so 4 e to the rx equals 0. Dividing through by e to the rx, we end up with r squared plus 4r plus 4 equals 0. Then we can solve this. We can factor. Then we have solution. R negative 2. The second r is also negative 2. This is two values, but they turns out to be the same. So we get, well, essentially, we have two values of r, but they are the same. So we should get one solution where 1 equals e to the negative 2x. If you use this and you say, well, y2 is e to the negative 2x as well, then that's not quite right, because it's the same as y1, right? So we cannot use it. We only have one solution from this method here. So to find a general solution, we need to know another solution. Later on, there is a rule whenever we have repeated root like this, then we can write out the second solution. But for now, I'll just ask you to check that y2 equal to x e to the minus 2x is also a solution. You may pause the video and try to do it yourself. The derivative of y2, we need to use the product rule. Then we have 1 e to the minus 2x plus x minus 2 e to the minus 2x. And we need to take the derivative one more time, minus 2 e to the minus 2x. And product rule here, we have plus minus plus 1 times minus 2 e to the minus 2x plus x times the derivative of this, we get 4 e to the minus 2x. We can simplify this. This is just 1 times this, so the same. So minus 4 e to the minus 2x plus x e, also 4 x e to the minus 2x. Now let's plug into the equation. We have second derivative minus 4 e to the minus 2x plus 4x e to the minus 2x plus 4 times the first derivative. First derivative is right here. We have e to the minus 2x, e to the minus 2x minus 2x e to the minus 2x. And lastly, we need to add 4 times the function, which is x e to the minus 2x in this case. And we want to know, does everything cancel out to get 0? Well, distribute and collect like terms, like what we're going to do. We have minus 4 e to the minus 2x here. And then you could look at this. We can combine them to get plus 8x e to the minus 2x. And then distributing plus 4 e to the minus 2x minus 8x e to the minus 2x. And we want to check this is 0. And suddenly we see that these two terms cancel out and cancel out. So we do get a true identity. So the conclusion is that y2 equal to x e to the negative 2x is a solution. Now, we know that y1, y2, but do we know that they are linearly independent? Y1, y2 linearly independent? Well, to do that, we need to look at the ratio. If the ratio is not a constant, then yes, they are linearly independent. But if the ratio turns out to be a constant, then they are not linearly independent. Look at the ratio. We have what? X e to the minus 2x divided by y1 is e to the minus 2x. So after canceling, we have x is not a constant, not a constant function. Constant function means you just have the constant. Here is x, not constant. So y1, y2 are linearly independent. And because of the theory, whenever we have two solutions that are linearly independent, they generate every other solution. So we have the general solution is y equal to c1 y1 plus c2 y2, which is in this case c1 e to the minus 2x plus c2 x e to the minus 2x. This is the general solution to the given ODE. And this formula captures all other solutions. Okay. Now to continue with this example, let's look at another pair of solutions. So consider again y1 is as before, but say y3 is minus 4 e to the minus 2x. The questions are y1, y3 linearly independent? Well, to decide this, you need to take the ratio, but this time we have the numerator minus 4 e to the minus 2x, denominator e to the minus 2x. They cancel out, and we have minus 4, which is a constant function, a constant. So no, they are not linearly independent. So as a result, they do not generate all other solutions. So they do not generate all other solutions. At the end of this lecture here, I want to mention one more thing that optional. So you don't need to watch this if you're not interested in. But here is in textbook or online, you might see a different way to verify that y1 and y2 generate all other solutions. So different criterion for checking that y1, y2 form a basis for the space of solution. Other books use something called the Wronskian, and the Wronskian denoted by W of y1, y2 is the determinant of this matrix 2 by 2 matrix y1, y2, y1 prime, y2 prime. And if you recall from your calculus 3, when you learned about cross product, the determinant is just you multiply these two together, y1 times y2 prime, and then you subtract y2 times y1 prime, subtract the product this way. And the criterion for y1 and y2 to form a basis for the space of solution is that if y1, y2 are two solutions such that the Wronskian W y1, y2 is not zero, then y1, y2 form a basis for the space of solution. So we have two different ways to determine whether y1 and y2 form a basis for the space of solution. This is to use the Wronskian, and the other one is just by taking the ratio and check whether it is a constant or not. If it is not a constant, then y1 and y2 are linearly independent. However, for us, we won't be concerned too much with Wronskian, so we won't use Wronskian very often.